Hello, Mr. McIver here, picking up on a query about one of the homework questions on circular motion. This is quite a tricky one, and I'll show you why. Here's the question on the page. It's number 4 on the circular motion check-in that I posted this week. And the thing to watch out for in this question is the very first line, in which it says a string has its ends attached to A and B. What this means is you've got one long bit of string between A and B. A is 4 meters vertically above B. A small heavy ring is threaded onto the string, and, next important bit, there is no friction. The ring describes a horizontal circle, center B. So this ring is whizzing round and round in a circle, level with the bottom end of the string. Now, if I draw this really carefully, here is what I get. There's A. There is B. That distance there is 4 meters. And the bit of string is such that it allows some point here, C, to be 3 meters out, exactly horizontal, so perfectly level with B. So that means my string is that. This is one piece of string that goes all the way down to there and all the way into there with this heavy ring C. And there is no friction. What this means mechanically is if I've got one bit of string there and no friction here, the tension at every point on the string is equal. So that is what the diagram looks like. I'm now going to mark up this diagram with all the forces on it, and then I'm going to answer the question. The way we always do these: resolve horizontally, resolve vertically, and hope it all comes out in the wash. So the first thing I'm going to do is call this theta up at the top, because that's what we usually mark in as our angle when what we have is it's a conical pendulum, but it's a bit of a weird one because this bit of string is extra long and it goes all the way down to here. We know that's 4 meters, we know that's 3 meters, therefore we know that that length there is 5 meters. It's a 3, 4, 5 triangle. That means we can instantly write down sine theta equals 3/5 and cos theta equals 4/5. That will come in very useful in a minute. But let's draw in our forces. I don't know what the mass of that is. I'm just going to have to call it M. So we've got a weight there, mg. What are the other forces acting on this object? Well, I suppose I must have some upward force there. What is delivering this vertically upward force? Well, the only thing I've got to deliver any vertical force other than this weight is this piece of string here. This string here, I've been told, is horizontal. Therefore, this tension here has absolutely no vertical component. Now, if I resolve T, I suppose I get going in the way T sine theta and going up the way T cos theta. So that must be T cos theta. To preserve this circular motion, I must also have a force acting in the way. It looks like the only force I've got here is T. But I've also got a bit of this T here acting in the way. So not only do I have the tension in the lower piece of string, I've got this other force of, going to have to draw it out here, T sine theta. So I just have one vertical force, but I've got 2 bits of my horizontal force, one being delivered by this string here, and one being delivered by part of the tension in that string there. I can now resolve vertically That's the easiest one to do because I've only got two forces to deal with, and I get T cos theta equals mg. But wait a minute, I know what cos theta is. That means that 4/5 of T equals mg. That means T equals 5/4 mg. Now I'm going to resolve horizontally. Now, I have a net radial force towards the centre horizontally because I've got circular motion. And what's delivering this force? Well, I've already seen. It's T plus T sine theta. So my total radial force towards the centre is T plus T sine theta. Now, using F equals ma, I can equate that to v squared over r. Oh, but I know what r is, don't I? And I know what t is too. So I can now, if I call this equation 1, sub in equation 1 into this equation. If I call that 2, and get 5/4 mg plus 5/4 mg times sine theta. Oh, but I know what that is. That's just times another 3/5 equals mv squared over r. Sorry, I made a mistake there. I just wrote in the acceleration component. It's mv squared over r. And immediately, all my m's cancel out. Now I can see that 5 times 3 is 15, 4 times 5 is 20, so that comes out as 15/20 mg. I can see that's 5/4, whoops, just g. I can see that's 5/4 g. Well, let's make it 20ths, so we can add these two things together. That's 25/20 mg. And that is simply going to be equal to v squared over r, which is 3 meters. This is now quite easy. 25/20 plus 15/20 is 40/20. 2g. 2g is v squared over 3. Therefore, v squared equals 6g. V equals the square root of 6g. This was a slightly tricky question. It looked like a two-string pendulum. It is sort of a two-string pendulum because you have two bits of the string, but because the thing is threaded on the string and there is no friction, we don't have two separate t values. The tension is the same at every point in the string, and that is what makes the question possible to do. If you found that one tricky, I hope you found that helpful.